Yeah, thanks very much. I'll keep this short so we can keep going. So I'm Derek Kanakin. I'm a principal engineering geologist here in our Kamloops office, and it's my pleasure to introduce John Danielson this morning. John completed his undergrad degree in geological engineering at the University of British Columbia and his master's in earth sciences at Simon Fraser University with Dr. Doug Stead. He joined BGC in 2009, and John's based in our Vancouver office. John is very much a rock engineering specialist, and he has a lot of international experience on very large and complex mining projects. He's been doing some really interesting work leveraging new tools and developing techniques to automate the collection and processing and validation of a lot of these large data sets that we use in the mining world. And I think today he's just going to share one example of how some of these modern tools can really help us free up time to get the geology right and focus on key engineering questions instead of being bogged down in just basic data processing. So over to you, John.
Wonderful, thanks, Derek. So I'm really excited to talk to you today about an AI workflow we've been developing for televiewer data processing. So AI has been in the news. There's been a lot of excitement recently, and a lot of that excitement is focused on things like ChatGPT and Bing AI Copilot, GitHub Copilot, these collaborative AI tools. And don't get me wrong, these tools are absolutely incredible, and actually they made the work that I did here a lot easier than it would have been otherwise. But those advancements have kind of overshadowed equally amazing advancements in the field of computer vision, where switching from a rules-based pixel by pixel comparison to a base founded in AI technology has really revolutionized the field. So computer vision, things like self-driving cars, you see it already with your automated login for Windows or your iPhone. It also makes things like augmented reality possible. But it's really gotten amazingly good at the four things I'm showing here. So image classification, saying, is this a dog? Object detection, saying, what's in the image and where? Instance segmentation, which is the application I'll be talking about today, which gives you a pixel level mask of what is in the image and where. And then semantic segmentation that aims to classify every pixel in an image. So my specific application for these AI-based computer vision technologies is televiewer data. So what is televiewer data and why does it matter? Televiewers are geophysical probes that we send down drill holes, and they survey the drill hole and give us an image of the inside of the drill hole. And we do this because it gives us information on rock mass fabric. So it gives us information on the orientation of joints, shears, and faults that cut through the rock mass. How we currently process it, we the traditional way before this tool, for each joint or discontinuity cross-cutting the image, you click along the center line 20 to 30 times, and then try to get a best fit orientation. If it's wobbly, you might have to start again. You have to do this hundreds and hundreds of times per hole. So it's incredibly time consuming. It's really boring. It's not a fun job. But it's something we do because this information is really, really important. And it's important because rock is controlled by the orientation and frequency and character of these rock mass fabrics. So in the example I have on the left, I'm a rock mechanics open pit specialist. So I'll give an open pit example here. So if you have bedding tipping out of the slope, you could get widespread failure where you have rock mass sliding along bedding. If this bedding was oriented differently, or if it had a favorable character, you might be totally fine. So because this is an an incredibly important factor. And because televiewer data is often our most widely available source of this data, and because it's a pain to process, we thought this would be a good test case for one of these AI tools. So one of the great things about these AI tools is they don't learn with logic. You don't have to feed it a set of instructions saying a discontinuity, rock mass fabric is something that's 30% darker from the pixels on either side. It has a sinusoidal shape. And you don't have to feed it a long list of exceptions. These AI tools learn by example. So all we have to do is prepare images. And we did that by taking the amplitude from televiewer data and coding it into the green and blue channels of the images, and taking the travel time and coding it into the red. So we're left with images like we see on the right, where we have this discontinuity where it's darker, and this particular one is open. So there's some red in the middle. So all we have to do is feed it images and labels. So we click and get outlines of each of these labels. And we started with a relatively small data set. We feed it into a model, and these models are often freely available, free to use. This particular one is open source. We use the YOLO, You Only Look Once, version 8 model by Ultralytics. So not only is it free, it's easy to use. And with just around 50 meters, so less than a third of our typical whole length of labeled images, we were already able to come up with good results for a test data set. And you can see that this discontinuity here, we get a pixel level mask, and we fit a sine wave to that mask to get the orientation. With just 50 meters of data, we're getting pretty good results for most discontinuities. I think the best way to train these tools is start with a small training data set, because you don't want to waste time labeling if you don't have to, and then seeing how it performs. And then based on how it performs, you can add more training data set, add more training, sort of targeting where the model is performing poorly. And so in this example here, this discontinuity in the middle, it's actually what the model's picking up. It's picking up two intersecting discontinuities, and it kind of loses its story. It jumps from one to the other. So what we did is we fed it more examples of intersecting discontinuities with high quality labels. So we went up to about 100 meters of training data, and then 150 meters of training data, until we felt we were at a good spot and the model was performing well. So the model's performing well. We're getting these orientations. That's all well and good. It could save us hundreds of hours per year. But for me, the most exciting part of this is those segmentation masks provide more than just orientation. And this is really exciting because some of these other types of information are really hard to do or really inconsistently done with current practice. And those are, so from the size of each of these segmentation masks, we can estimate aperture, how wide a discontinuity is. From the shape of the mask, we can estimate roughness. From the amplitude, so the green and blue channels that we've coded into the images, we can get an estimate of infill strength because amplitude correlates with strength. And then from the travel time, which we coded into the red channel, we can get an estimate of whether that joint is open. And these are all things that technically could be done by human loggers, but it would take forever. We would do it really inconsistently, so we generally don't do it. Or in the case of aperture, we do it for wider structures, but everybody has a different understanding of what they would call a wider structure. So the data is actually really hard to use unless you're talking about really wide structures. But with this tool, we can get an estimate for every single discontinuity that the model finds. Just to talk about roughness briefly here. So roughness is important because going back to our example at the beginning, when we were talking about sliding along these beds, you can imagine if these beds were actually discontinuous and really rough and tight, you might not have an issue at all. But this was like previously we get estimates of roughness from a sleep-deprived logger in a core shack at 3 a.m. and his description of roughness might vary from the day shift logger. So it's really a difficult data set to work with. But the tool is consistent. The AI tool is consistent. And we can get roughness really easily by taking that mask, skeletonizing it, so finding the center line, and then subtracting the fitted sine wave. And we're already fitting the sine wave, so this adds almost no time to the processing. And we get roughness profiles. And you can see that along this one, there's a bit of a jag here that corresponds with this jag in the roughness profile. And it does this almost for free for every discontinuity. Okay, so that sounds good, but how does it compare with other sources of data? So I have our AI tool picks shown here. It gets 4 of the 4 open discontinuities that I would have logged. We compare it against results from an automated logging tool that's provided with the logging software. And I'll say this logging tool is actually really sophisticated, and it's a pretty impressive tool, but it uses the traditional image processing techniques, rules-based. And so when there are things like horizontal lines from drilling or artifacts in the image, it picks those up as false positives. So it does a pretty good job for 3 of our 4 discontinuities, but it also picks up a lot of noise. And then we see the manual loggers here. They get all 4, but they also pick up something which I would not consider to be geotechnically relevant. Just one more example, the AI tool gets 1 of 1 real geotechnically important discons. The auto logger picks up a ton of false positives. And then the manual log also picks up false positives, which I would not consider geotechnically relevant. So aggregating all that into a single plot, these are stereo nets. You don't really have to understand too much about them except that they show the distribution of orientations. And we get pretty good agreement actually between the AI results and the manually logged data. So the biggest concentrations are these sets here. But you'll notice because the manual loggers were picking up all these faint hairline discontinuous features, you get a lot of noise. So the resulting stereo net kind of looks like a donut. You get discontinuities of every orientation. Whereas in the AI results, which aim to pick geotechnically important features, we really see the sets come through more clearly. So the automated logging tool, although we've seen that it can do really well for certain discontinuities, because it's picking up those horizontal drilling artifacts, it kind of washes out the entire story. So I'll just leave you with these 2 thoughts. One, I want to sort of proudly say that our AI-powered workflow lets us save hundreds of hours per year, process data in less than 5 minutes instead of hours, with what I would call human-level accuracy and perhaps superhuman-level consistency, with a caveat that we still need to go through the review process, and this might not work for all types of data. And it lets us get consistent estimations of things like roughness and aperture, which were previously too difficult to get when it's logged by humans. And the second thing I want to impress is that these models are really easy to use and take advantage of. So we don't have to come up with a detailed rubric. We just have to feed these models images and labels, and they learn by example. So I hope folks are thinking about different ways that they can take advantage of these for other applications. So that's it. I'll see if there are any questions in the Q&A.
There is one there from Luke, John. If you see that one. Yes.
So is the YOLO model pre-trained and you just had to retrain the last dense layer, chance for learning? So I did. I did start with a pre-trained model, but it's trained on things like dog, cat, bicycle. So I didn't just retrain the last dense layer. I set each of the layers sort of to freely adapt to our specific application. But even so, it's best to start with the pre-trained model on, in this case, like the COCO, the massive data set, because it gives the modeling an idea of what you can work with. Was someone else talking?
They might come back in. I see Paul's got his hand up for a question though.
Paul, do you have a question?
We'll let Paul ask that question offline just so that we can keep moving along on our schedule here. Thank you so much for the presentation, John, and Derek also. As with others, we will post their email